So our next topic is this higher order derivatives. We have already seen that if you have a function, say y is equals to f of x, then we differentiate it and say dy by dx, which is actually represented as f dash x or even y dash. So this we have already seen. Now if this is differentiable, then we can differentiate f dash x as well. So differentiating once again, what will happen? Now I'll have differentiation, that is again with respect to x, of dy by dx. So that is shown as different notations are there for this. One of them is d square y by dx square. This shows that it is second order derivative, or we show it as d2y, or we also show it as y double dash, or f double dash of x, or even y2. So these are different representation. They are not different formulas or different methods. They all represent the same thing, and this is called second order derivative. In same way, if even this is differentiable, then you can differentiate it again. So the next level will be what? Next level will be the differentiating the first function thrice. The thrice. So it will become d cube y divided by dx cube, or you can represent it as d cube y, or you can represent it as y triple dash, or f triple dash x, or y3. So now this is third order derivative, and same way there can be nth order derivative. So this one is third order derivative. So that's all in this higher order derivative. I mean, the concept wise, only this is the new concept. Now the rest of this, the rest in this topic is just practice. So we'll now practice some questions in this or on this topic. So we have been given y is equals to x cube plus 10x, right? So this is y. We have to find d square y by dx square. This we have to find, right? So what we are going to do first we are going to differentiate with respect to x. That will be the first order derivative. So differentiating it once will give you first order derivative, that is dy by dx. So what will be that? That will be 3x square differentiation of x cube plus differentiation of 10x is nothing but secant square x. So this is our second order derivative. Sorry, first order derivative. Second order derivative means you differentiate it once again, right? This will give you second order derivative, which will represent as d square y by dx square. That means now you have to differentiate this once again. That is d by dx of 3x square plus secant square x, right? Okay, now this is little tricky than the previous one. So differentiation of 3x square is simple, that will be 6x. But secant square x, here we'll have to apply the x to the power n formula, and then some function to the power n formula and then differentiation of that function. So first it is 2 into secant x and then differentiation of secant x. So we are applying the chain rule. So this is 6x plus 2 secant x into secant x differentiation is nothing but secant x plus, sorry, secant x into tan x, right? So simplify it, 6x plus 2 secant square x into tan x. So this is our final solution. That is if we are finding only the second order derivative. Now suppose you had to find the third order derivative. That is, you have to find d cube y divided by dx cube. So in that, what do we have to do? We have to now differentiate this once again with respect to x, right? That means we have to differentiate this function 6x plus 2 secant square x into tan x. So now we have to differentiate this. Differentiation of 6x is simple, that will be just 6. Next is again little complex. So here you have to apply the product rule. So 2 secant square x d by dx of tan x plus tan x into d by dx of 2 secant square x, right? So this will be 6 plus 2 secant square x into secant square x plus tan x into 2 into differentiation of secant square x, and differentiation of secant square x we have just done. No, we haven't done. So that will be 2 secant x into secant x tan x. So secant square x, because it is square, secant to the power n, so it will be n into secant to the power n minus 1. So 2 into secant to the power 2 minus 1, that is 1. And then differentiation of secant x, which is secant x tan x. So now this complete is 6 plus 2 secant to the power 4x plus 4 tan square x and secant square x. Right, so that is the final answer. That is if we have to find the third order derivative. So this is the third order derivative. Before that, it was second order derivative, and this was the original function, that is x cube plus tan x. Okay, let's move to next question. So we have been given y is equals to some a sin x plus b cos x, right? And we have to prove that d square y by dx square plus y is equals to 0. So again, as you can see here, what do we have here? We have a second order derivative. So that means we have to find the second order derivative. So for that, first find dy by dx, that is equals to a cos x minus b sin x, right? Now in our question, we have to prove that this d square y by dx square. So that means we have to now differentiate it again. So what will be that? That will be minus a sin x plus b cos x. And what do we have to prove? And if you see this minus a sin x plus b cos x, this is actually equals to minus y, because y is a sin x plus b cos x, right? So this is minus a sin x minus b cos x. So from this we can say that d square y by dx square plus y is equals to 0. This is what we had to prove. And from here, this second equation itself, we can prove that. Why? Because d square y by dx square is minus y. So that means d square y by dx square plus y is equals to 0. Right? Let's move to next question. In our next question, we have y is equals to 3 into e to the power 2x plus 2 into e to the power 3x. And what do we have to do? We have to prove that d square y by dx square minus 5 dy by dx plus 6y is equals to 0. So we'll go normally, that is, in the final expression we have to find d square y and dy by dx both. So that gives us a hint that we have to start finding the differentiation. So first is dy by dx. That will be actually 3 into 2 e to the power 2x right, and the second term is again 2 into 3 into e to the power 3x. So that is actually equals to 6 into e to the power 2x plus e to the power 3x. That is dy by dx. What do we have to do next? We have to next find d square y by dx square. And whenever we have to find the second order derivative or third order derivative, so we try to keep this in the simplest form so that finding derivatives is easier. So what is this? This is 12 into e to the power 2x 12, right? E to the power 2x differentiation will be e to the power 2x into 2 plus 18 e to the power 3x, that is d square y by dx square. In this, I can take again 6 common and I will have 2 e to the power 2x plus 3 e to the power 3x. Right, that is d square y by dx square. Now what do we have to do? We have to prove this. So now we have all these unknown variables, that is we have d square y by dx square, we have dy by dx, and we also have y. So now just substitute that. So d square y by dx square minus 5 dy by dx plus 6y. What is this equal to? So this is equals to 6 into 2 into e to the power 2x plus 3 into e to the power 3x, that is d square y, then minus 5 into 6 into e to the power 2x plus e to the power 3x, right? And plus 6 into y, which is 3 e to the power 2x plus 2 e to the power 3x. So this is equals to 0. What do we have to do? We have to prove that this is equals to 0. So this will come to be 0 because you can say e to the power 2x, right? There are 12 e to the power 2x, and yeah, so there is 12 here and 18 here and 30 here, so on. Then we have 18 e to the power 3x plus 12, 15 e to the 50 e to the power 18 plus 12, so total 30 e to the power 3x, and here also we have 30 e to the power 3x, right? So all good, it is 0 as expected or as desired in the question. This is 0 and we have proved that. Just wait for some time. Yeah, so that was the previous question. Let's move to one more question. We have y is equals to sine inverse x. So these are different type of questions, and you should be familiar with all these different types so that in exams you don't find something very new. Okay, now in this case, what do we have to do? We have to show that 1 minus x square into d square y by dx square is minus x dy by dx is equal to 0. So let's solve this. Y is sine inverse x, so that is straightforward. Dy by dx. Dy by dx is 1 divided by root of 1 minus x square. So that is dy by dx. Now you will be seeing, okay, here we can differentiate it, but differentiating it will not be that straightforward. So it is better to apply some transformations here itself. So I can actually multiply this or do this cross multiplication, 1 minus x square into dy by dx. And now you can see a dy by dx is also a function. So into dy by dx is equals to 1. Now if you see this carefully, there are two functions. One is this function and another function is this. Both are functions. Dy by dx is also a function, which is clear here. Right, so that means now this is in the form of uv, and uv dash is equals to u dash v plus uv dash. So now apply that rule here. So first one is differentiation of the first function, that is d by dx of 1 minus x square into dy by dx plus root of 1 minus x square as it is, and into differentiation of second function, that is d square y by dx square. Now this, and on the right hand side there is 1, so differentiation of 1 will be 0. Okay, so now we just have to differentiate this first function, that is d by dx of root of 1 minus x square. So that is nothing but differentiating of any root is this. So even this will be 1 by 2 root 1 minus x square. And then what? Then you have to differentiate 1 minus x square. So if you differentiate 1 minus x square, you will get minus 2x into dy by dx plus that's all root of 1 minus x square into d square y by dx square is equals to 0. Now in this case, this 2 and 2 cancels. So we have, if I can change the order here now, that is write the d square term first. So this will be root of 1 minus x square d square y by dx square minus x divided by root of 1 minus x square into dy by dx is 0. Now you compare it with what you have to prove. We have to prove this expression. So we have to somehow write to this, and we are almost there. We have minus x dy by dx just like this, and we have root of 1 minus x square dy by dx. So but there is root of 1 minus x square in the denominator of the second term, that is here. So now we think about doing cross multiplication. So that will be 1 minus x square whole square d square y by dx square minus x dy by dx is equals to 0. So this is what we actually had to prove. What we had to prove was this 1 minus x square d square y by dx square minus x dy by dx is equals to 0. Let me know if you think that you have some problem or you are not able to understand. And this is not the only way of doing this. You can even solve it in some other way as well. So if you want to do it like this, say y is equals to sine inverse x, then you have differentiated it once, say y dash, that is equals to 1 by root of 1 minus x square. So from here, what we can say is 1 minus x square into this y dash so what we have done is we have taken square on both sides. So if I do that, I have y dash square is equals to 1 by 1 minus x square. Right? So this can be written as 1 minus x square into square of y dash. So this is equals to 1. So from this, I can say this will be 1 minus x square into 2 y dash into y double dash, right? Plus this y dash y dash square, the second function as it is, into minus 2x. Again, if we solve this, we have y dash. Here there is 2y dash, here there is only 1y dash, so y dash can be taken as common, and in the first term you will have only y double dash. So the first term becomes 1 minus x square into 2y double dash minus 2x into square of y dash. This is equals to 0. And again 2 common. So what do we have is 2 common, and sorry, even this is out of this 1 y dash we have already taken. So in the end there is just 1 y dash. So taking 2x common, we will have 1 minus x square into y double dash minus 2 is gone, x y dash is equals to 0. So that was about the higher order derivatives. Now this brings us to exercise 5.7. So complete that exercise, and the next topic is the last topic in this chapter, that is Rolle's theorem and the mean value theorem. So we'll do that as well, but before that I want you to solve some problems on this exercise, and yes, and some more problems I'll